Wow, it was really interesting to hear all of your analyses on your individual sites. And I'm going to do something that maybe has a little bit of a different perspective. We're calling it a deep dive into the data. I'm going to do a combined site analysis, and I'm going to talk first about what kinds of research questions we have in this analysis, what kind of methods we use, and finally the results and the interpretation. So the strategy, your strategy for finding your stories was an individual site analysis, and the volunteers are finding the stories by exploring questions like what you'd looked and what questions you asked were, how healthy are our sites as indicated by the water quality parameters? Are any water quality criteria violated? Are there any outliers? What seasonal patterns exist? Are there deviations from those patterns? How do the patterns of various parameters compare to one another? And can we identify factors that may have influenced our results? So you all did that tonight. I think most of you hit on every single one of those research questions for your individual site. So these are the sites that are in the data set that we're looking at right now, the Stream Team data set. There's 61 of those sites. And you guys were looking at each of those sites individually. Now, the strategy that I'm taking, which is simply layered on top of your strategy, is exploring relationships between watershed attributes and the stream water quality characteristics by using data from all the sites. And I'm exploring questions such as, does land use and geology in the watersheds impact the water quality in the streams by using all of the sites? And if so, how does it do that? And can we identify causative factors for differences in water quality between groups of sites that have similar attributes? So in a sense, I'm taking more of a bird's eye view. And if these are all the individual sites that you guys are doing the analysis for, I'm trying to look at all of the sites together as a single study. Okay, so those are the research questions. So bear with me while I go through the methodology. And I'll do the best I can to get through it quickly and efficiently, but enough so that you can, I think, appreciate what we're trying to do. And I know for some of you, this is old hat, and for others of you, you probably haven't heard this stuff before. So I'm going to look at three things. First of all, how did we generate hypotheses? What were we thinking about when we generated hypotheses regarding potential relationships that we wanted to test? How did we organize our master data sheet? And then finally, what were the statistical techniques that we used? I'm going to talk about box and whisker plots, which if you've come to former workshops, you've heard about that a bit. And then also regression analysis, which is a very common method that I know a lot of you have experience with. So first of all, generating hypotheses, what are we talking about? What kinds of relationships are we interested in exploring? So we want to generate hypotheses regarding relationships between watershed attributes and stream water quality squares. So if you look at the diagram here, watershed attributes are geology, the carbonate, the non-carbonate, and the land use, the percent developed, ag, and natural. And these are the attributes that were delineated in the GIS that the Alarm folks delineated for each individual site. And we want to take a look and see overall, do these parameters impact these water quality parameters that you guys measured in the field? So here are two examples of hypotheses that we could test. As development increases in our watersheds, the median values of conductivity increase. That's a hypothesis. It makes sense. Does it really happen? Can we demonstrate with our data that this is what happens? Another hypothesis could be, as the percent carbonate geology increases in our watershed, do the median pH values increase? And so if we find there's a relationship, then we also want to explore the strength of the relationship. So those are the kinds of hypothesis generations that we've been doing. Now, here's the master data sheet. I think it's just useful to look at this partly so you can appreciate the volume of data that you all are producing, and also so that you can understand how you can step back and rather than looking at individual patterns, you can look at larger patterns and relationships between sites. So we have here the county, and unfortunately on my screen, I can't see these headings, but then the site ID, latitude, longitude, and so on. The light green column headings are the watershed attributes, things like the size of the watershed and the land use and the geology. Whereas the blue, the turquoise column headings are the water quality parameters that you guys measured in the stream. And we're looking at things like what is the median conductivity at each site, the median nitrate, the median pH, and it goes on. I'll talk a little bit more about the IQ temp later on. The sites on this sheet, I have sorted them in terms of decreasing carbonate percentage. So if you look at this column where my cursor is, you can see that it goes from 100% carbonate all the way down to 0%. This whole spreadsheet then has been sorted according to carbonate. And then the sites have been color-coded into groups based on how much carbonate is in their stream watershed. So we have the high carbonate groups, we have the medium carbonate groups, and the lower carbonate groups. The next spreadsheet is the same spreadsheet, but what we've done here is we've sorted it in order of development, the percentage development, and we've divided the groups into the sites into 4 groups. These are the high development sites, or the sort of yellow here, the blue are the medium high, the green are the medium, and the peach are the low. So this is the kind of analysis we're doing, looking at sites based on their attributes and then grouping the sites so that we can look at groups and see how one group relates to the other group. So let's talk about box and whisker plots so you understand how to read these. And again, I'm sorry if this is repetition for those of you who have done this before. These plots are really cool. I like box and whisker plots because they show the distribution of all the values of the variable in one little diagram, and it's very visually illustrative. So I really like them. So how do you make box and whisker plots? You take all your data, and your maximum value is up here. That's your top whisker, your maximum whisker, and the bottom is your minimum value. And then your central tendency, your median value or your mean values are somewhere in the middle. The important thing is this box. And this box here, you can think of it as that is the area that contains 50% of the data in your data set. So if you're looking at conductivity, that contains 50% of your conductivity values. And so if you come over here and you look at 2 box and whisker plots, you can see that the blue one has a fatter box or a higher box, a bigger box, as it were, than the orange one. So that means that on the orange site, whatever it is you're measuring, there's not much variability. 50% of your data points fit within a very narrow range. Whereas in the blue, you have quite a bit of variability. Your box is bigger. So box and whisker plots can tell you about variability, and they can also tell you, of course, about the absolute values. For example, the blue box, and just as an example, the maximum, the top whisker, is actually lower than the orange box's minimum. And so the orange has higher overall values, but they don't have much variability, whereas the blue have lower overall values, but they have quite a bit of variability. So these are all things that we're going to look at. Let me show you a real example. This is data that you guys collected from the Conductivity. This is water temperature, and these sites here are 6 sites as you go downstream that have quite a bit of variability in water temperature. Look at how long and drawn out those boxes are. But then there's these 3 sites up here that have much less variability. And if you look closely, you'll notice that these 3 sites are actually mostly limestone sites, whereas these sites are mixed geology sites. And these sites have less variability. And you'll also notice that the maximums are lower than these sites and the minimums are higher than these sites. So you have a typical limestone pattern where you have less variability and your winter highs or your winter lows aren't so low and your summer highs aren't so high. And so box and whisker plots show this very, very nicely. Here's another example, and this is actually from the data I'm going to show you today. And this is looking at groups of sites. The orange are sites that are highly developed, and then medium developed, and then medium low, and then finally low developed. And we're looking at conductivity, and you can see very clearly that although the variation is pretty similar, the variability is similar in those four groups, that the highly developed sites are showing much higher conductivity. And as you go down, you step down into the less developed sites. More on that later, just trying to illustrate box and whisker plots. Okay, so now we get to regression analysis. So regression analysis is used to examine the relationship between two variables. And this analysis determines how the variables are related. Are they inversely related to each other or directly? In other words, as one increases, does the other increase, or as one increases, does the other decrease? And it also looks at the strength of the relationship as well. So to evaluate this relationship, we plot all the points on a bivariate plot, and I'll show you this in a minute, and we draw what's called a best fit line. And then we use a value known as R squared, or regression coefficient, to evaluate how tightly the points cluster around this line. If you don't understand this right now, if you haven't done regression, it's going to be clear, I promise you, in a minute or two. The tighter the fit, the stronger the relationship. R squared goes from 0 to 1. If it's 0, there's no relationship. If it's 1, it's a perfect relationship. Now, in very complex natural systems like streams, the R squared values between any two variables tend to be relatively low because there's so many other factors that may affect any one variable. So what do we mean by all this stuff? Let's get away from streams for a minute, and let's talk about something completely different that's easier to imagine, perhaps. We're going to talk about the relationship between age and height in children. So we have here's our data. We have 26 children, and here are their ages from 2 to 12, and here are their heights. We take that data and we plot it, age on this axis, height on this axis, and every one of these points is a child, correct? And that child is defined by its age and its height. So we plot it in age, height, space. Then we draw a line that is the best fit for those points. Okay, and that's the line there. That's called a trend line or best fit line. And then how good is that fit? We calculate an R squared value. And in this case, it's 0.9016, which shows that there's an extremely strong relationship between age and height. And that age, the variability in the age, can actually explain quite a bit about the variability in the height. Not everything, but quite a bit. And one way to look at an R squared value is if you change that decimal into a percentage by moving that decimal point over 2, it's 90%. That means that the variability in age can explain 90% of the variability in height. 10% is due to other things. Okay, let's look at some more data on these kids. All right, here's your children. Let's look at this one, the ages, and we're going to look at how many hours they sleep. And there they are there. So we plot this data on age, hour, sleeping space. Each one of these points is a child. And you can see, this is a little bit different. This is going in the other direction. It looks as though the older they are, the less they sleep. Let's see how good a fit that is. There's our best fit line. And here's our R squared value. Well, R squared value is only 0.51, which is okay. But what that's saying is that variability in age can only describe 51% of the hours that kids are sleeping. That the other 49% is due to other things. And finally, we're going to look at the same kids and the age and the miles traveled per week. And we can plot them in age, miles traveled per week, space. And these are all the kids plotted there based on those characteristics. We put in a trend line. It doesn't really go up or down. It's kind of horizontal. And look at that R squared value. It's very, very low. Only 0.3% of the variability can be explained by age. It's virtually useless. So we consider that not much of a relationship. Okay, let's apply this to our data. Go back to streams, and here's our data. Here's our site IDs, and what we're going to take two variables. We're going to do the percent developed against maximum temperature. that might be an interesting hypothesis is, as development increases, does the maximum temperature that we've been measuring, does that also increase if we look at all the sites? And so all these points, each point, these are 61 points, each point is a site, percent developed, does it impact maximum temperature? R-squared value, pretty low, probably not. Okay, and what this is basically saying is the variability in the percentage of developed land in the watersheds can only explain about 3.2% of the variability in maximum temperature. So it's not particularly useful. The higher this percentage, the higher the R-squared value, the better predictor one variable is of another. So basically what we're saying here is that percent developed in the watershed is not going to be a very good predictor of maximum temperature. Too complex. All right, I'm done with the methodology. We're going into our results, and I'm very happy to be done with methodology, and I think you're going to like the results because they're really cool. Okay, first thing we looked at, does land use in the watershed significantly impact conductivity concentrations in the streams? All right, so here's our regression curve, percent developed against median conductivity. And you can see that as development increases, median conductivity tends to increase. The R-squared value is 0.4084. So 40%, that it means that variability in the percentage of developed land watersheds can explain 40.8% of the variability of conductivity values. Well, given the complexity of aquatic systems, that would be considered to be a strong R-squared value. I was actually surprised that it was so predictive, in a sense that developed is so influential in terms of determining conductivity. And again, if we look at the different groups, the highly developed to the low developed in box and whisker plots, if you prefer those because they're so much more visually appealing, you can see that you step down as you go into less developed. You do get the distribution of the median conductivity values in those groups is much less than the distribution in these groups. Medians are less and so on. Variability isn't that much different. Okay, so if that's the case, how about ag? Let's look, does the percentage of agriculture in all of our sites, can that predict median conductivity? And in fact, the answer is no. Agriculture doesn't have nearly the close relationship to median conductivity as the developed does. And so that was kind of an interesting conclusion. Now, looking again at our data, does the land use in the watershed significantly affect nitrate concentrations in the stream? Well, let's look at agriculture. Here's the percentage of agriculture. We normally think of agriculture as having an impact on nitrates. But if you look at the data, I mean, I gotta admit, when I looked at the data, just kind of eyeballed the data, I couldn't see anything that looked like a pattern. But if we look at median nitrate and percent agriculture, we do indeed see that there is some predictive value there. There is a relationship there. And here's our box and whisker plots from the highest percent agriculture to the lowest. And nitrate does make a difference. The higher nitrates are definitely in the higher ag sites, and the lower nitrates are in the lower. Now there are some outliers and so on. So does the same thing happen, for example, with percent developed? And in fact, the answer is no. If you look here, percent developed doesn't have nearly the impact on, or the relationship, the tight relationship, the close relationship, the predictive relationship with nitrate as ag does. So that was really interesting. Okay, does geology significantly impact median conductivity? And so we looked at percent carbonate against median conductivity. And as you guys, many of you mentioned this in your talks, indeed, there is a relationship there. And here are the box and whisker plots. The variability of the percentage of limestone in the watershed can explain 37.2, a little more than a third of the variability of the conductivity readings. The other 2/3 are due to other things, but that's still an important influence. Now, does percent carbonate does that have a relationship with nitrate? And the answer is, not really. It's not really high enough to make much fuss about. All right, now does geology or land use significantly impact temperature variability in our streams? Let's look at geology. So what I used for temperature variability was the size of the box. Okay, in the box and whisker plot, it's called the IQ range, the interquartile range. I used the size of the box. So it looks as though as percent carbonate in the watershed increases, the size, the variability of temperature does in fact decrease. It's not terribly strong, but it's getting there. It's about a little more than a quarter responsible for that. Okay, and if you look, what's I think even more interesting, if you look at the groups and you look at those, these are all the sites with greater than 50% carbonate, and these are the sites with less than 50% carbonate. And this is these aren't box and whiskers, these are just bar graphs. This is showing that the mean, this box, the size of the box or the interquartile range is only 6 if there's a lot of carbonate, whereas it's 12 degrees if there's less. So that's showing there really is a difference, and carbonate does have an impact on decreasing the variability of temperature. Does land use have an impact? Here's developed, here's a natural, which I threw in there, and the answer is no, it doesn't have an impact. The land use is not really impacting temperature variability nearly as strongly as the geology is impacting temperature variability. And finally, we get to the last thing you measured, which is the pH in our streams. And let's explore that a little bit. Does the geology impact the pH? And if you do a regression curve of percent carbonate and median pH, you get a fairly low R² value. It doesn't look like very much. But then if you go in and look a little closer, you can see there are 3 sites here that I circled. And those are sites where the pH, median pH, is less than 7. And all of them are in 0 carbonate watersheds. But there also are sites in 0 carbonate watersheds that have higher pHs as well. So I decided to look at it a little bit differently. I decided to look at it with box and whisker plots. And that I thought was even more interesting, because the blue one is the greater than 50% limestone or carbonate, and the orange is less than 50%. Look at the difference there. There's not much variability in the limestone with pH. And there's no outlier for maximum or minimum. It's all scrunched in together there between 7.5 and 8. Whereas the non-carbonate streams are pretty much, there's much more variability. There's high ones, there's low ones. And so at least what we can say geology is not a strong predictor of pH, but it's clear from all of this data that we've collected that carbonates do buffer streams, and they thereby preventing low pH and resulting in less variability in pH. So that I thought was kind of interesting. And then finally, does land use impact pH? And I got to tell you, folks, I couldn't find anything here. I found that R² values are low. The box and whisker, our data do not show a strong relationship between land use and pH. Okay, so let's summarize a little bit here, and then I'm almost done, so hang in there. So I want to remind you that these findings are based on stream team volunteer data from 61 sites. Each were monitored monthly for approximately a year for conductivity, pH, temperature, and nitrate. You know that better than I do. In addition, the watersheds for each site were delineated, percentages of developed agriculture and natural land were measured, and percentage of land underlain by carbonate or non-carbonate geology were measured. So it's a big data set with a lot of data. And the relationships that were particularly notable were the percent developed and conductivity, and these are the R² value. The percent agriculture and nitrate have a close relationship. Carbonate and conductivity have a close relationship, and carbonate and temperature variability have a close relationship. Our data, your data that you were able to collect has shown that. We were able to demonstrate also that the presence of carbonates buffer streams against variable and/or low pH. So I want to tell you, I think this is really cool. I think basically what we have here is these results are empirical evidence for all these theoretical hypotheses. And you can only get that kind of evidence if you have a very large and diverse database. And that's what you've been able to correct. So let me praise volunteer monitoring. Large data sets, and our data set that we used here is over 4,500 data points on numerous streams, 61 in this case, that are geographically diverse, 5 Pennsylvania counties, and densely sampled through time monthly, are rare. Only trained volunteers can collect this size database in a cost-effective manner. Can you imagine what it would have cost to have sent, a state employee out to collect all this data that we've been able to collect? It's just simply not cost-effective. So the relationships that these data demonstrate, or the stories that they tell, they really do tell congruent stories. That lends credibility to the accuracy of the volunteer data set. So I will say that this is a tribute to the effective training of volunteers, the appropriateness of the methods used, and the quality assurance, quality control program. And more importantly, it's a tribute to the commitment and perseverance of the volunteers to assure consistency, completeness, and accuracy of the methods and results. So all I can say is, congratulations. I mean, these are just, I think these results are important. I think they're interesting. And I think the more data we can collect, the clearer we're going to be able to get a picture of how our streams are behaving and how land use, geology, and other factors, at some point dischargers maybe, are affecting these things. Let me just do a footnote. I didn't explore all the relationships we can explore in all the ways in which we can explore them, and I don't want to represent that I did. I just did a little tiny subset of data exploration. So if you could think of other things to do, and are there stories that are yet untold and so on, we would love to hear about that, share it with us, and see if we can, do some work in other areas as well. There are lots more questions we could ask.